All right, let's talk a little bit about alkenes, and we'll talk about alkene nomenclature just a little bit as well, and a little bit of reactions. The alkenes are hydrocarbons that contain carbon-carbon double bonds, where the simplest alkenes would be ethene or ethylene, and propene. The common names, again, ethylene, and you can call it propylene. Alkenes are named in the same way as alkanes, except you change the E and E suffix, replacing the A and E suffix. The double bond location would need to be indicated by a number. Now, while you didn't really get it with an alkane, you can get geometrical isomers with a carbon-carbon double bond because you don't get rotation around the pi bond the way you do a sigma bond. If they're on the same side, then they're cis, and if they're on the opposite side, they're trans. You probably hear that with cis and trans fat as well, and it is certainly this. So, and the reason it works is you have what they call restricted rotation. You can't rotate. And the two groups on the left-hand end of the bond and two groups on the right-hand end, it doesn't matter really as long you're looking at the same side or the opposite side. So it doesn't matter whether they're both on, let's say, the left or the right or the top or the bottom, or depending on how the molecule's oriented. Now, if you were to rotate that carbon-carbon double bond that is moving from cis to trans at 90 degrees, you would break that pi bond. And that's why you generally don't get rotation. You don't readily shift from cis to trans. Is it 100% impossible? No, but it's unlikely in most situations. Now, geometrical isomers have the same formula, the same connectivity of the atoms. So they're not structural isomers, but there's a different three-dimensional spatial arrangement of those atoms. If you have more than one double bond, we call it a diene. If you had three, we call it a triene, so on and so forth. So if we look at this, this would be, the first one would be 2-methylpropene. Now that is not a cis-trans isomer because the methyl groups are both attached to the same carbon. Now we got 1-butene, and again, 2 hydrogens are on the same carbon. So you don't really get cis-trans isomerism there as well. But for the 2-butene, you can see you get cis-2-butene and trans-2-butene, where in the cis, both the methyls are on the same side, and on the trans, they're on the opposite side. So we have cis-trans isomers. 2 different molecules, same formula, same conductivity of the atom, same positioning of the double bond, but they're on opposite sides and they can't readily switch. So that is cis-trans isomers. If you get a double bond, you do get that pi bond overlapping, say, above and below the plane of the sigma bond. Sigma bond, remember, is head-to-head overlap. Pi bonds are side-to-side overlap, usually occurring to the top or the bottom or the front and the back of the sigma bond. Alkynes, a lot of the nomenclature works exactly the same, except you get a triple bond instead of a double bond. Alkynes have 1 sigma and 2 pi bonds between the 2 carbon atoms equaling a triple bond. Ethine or acetylene is probably your most commonly encountered alkyne. And so that has a common name acetylene, but its technical or IUPAC name is ethine. You don't get cis-trans isomerism with alkynes because you're at a 180-degree bonding and there's no way to be on the same or the opposite side. Acetylene is burned, it produces oxygen, or reacts with oxygen, produces a flame 3200 Kelvin, and they'll burn the same way as alkenes, just like a typical combustion, like the alkanes would do as well, as we talked about. So we're going to talk about drawing some structures of compounds now. So we'll stop the share and go to the paper. 1,3-butadiene. So it's a butane. So 1, 2, 3, 4. And so 1 means it's going to be there. 3 means it's going to start between 3 and 4. And so 2, 1, 1, 2. Or some people draw it more like this, where you've got a double bond here and here. Either way, you have 1,3-butadiene. So the double bond is numbered based on the bond where the atom where the bond starts, not where it finishes. 2-pentyne. So we're going to get 5 carbons. If it's pentyne, so that means it's going to be a triple bond here. So that's going to be CH3, no hydrogen, no hydrogen, CH2, CH3. Now we get pentene. So we're going to start with our double bond because it's a cis. And it's cis 1, 2. So this would be the end of our molecule. So the fluorines would be on the same side. It doesn't matter how you draw it to represent the same side. And so you'd have hydrogen there, finishing out the octet. But down here you would have 1, 2. So you need CH2, CH2, CH3. Finish out my pentene 1, 2, 3, 4, 5. But this shows the cis-trans type structure. In this case, it's a cis. If it were trans, these two groups would be flipped, for example. Now, let's look at some structures then and see if we can name these. So I've got a double bond there. So the longest chain has to include the double bond. 1, 2, 3, 4, 5. This isn't going to give me anything. But so I'm going to number it 1, 2, 3, 4, 5. I've got a methyl group hanging out on 3. So it's going to be 3-methyl and double bonds between 1, 2. So it's going to be 1-pentene. Here I've got a double bond. Let me see. We got 1, 2, 3, 4, 5, 6, 7, 8. The double bond goes between 1 and 2. I'm going to give the double bond the lowest possible numbering. So it's 1 octene, indicating the double bond is at location 1. It could be here or here, for example, and I would change the numbering of the double bond. Prioritizing the numbering of the triple bond, 1, 2, 3, 4, 5, 6. So it's going to be a hex -ine. It's going to be a 1 hexane. Sometimes people put the number back here, particularly on more complicated structures. But so it's going to be 1, 2, 3, 4, 5, 6. So it'll be 5-methyl 1 hexane. And that would be alkenes and alkynes. And for our purposes, since it's a general chemistry course, we'll stick to the simple ones. All right, let's talk about reactions of alkenes and alkynes. The most dominant reaction involves addition of something to the double or triple bond. You get hydrogen, or we get add halogens, or we can add a binary acid like HCl or HBr, or we can add water. Hydrogen usually requires a catalyst, like platinum in particular works well, but nickel and palladium can work as well. And so we're going to do some addition reactions where we add hydrogen, bromine, HBr, and water to ethylene. So let's stop our share and we'll write those particular reactions. So we're going to write our ethylene is this. Now I'm just going to do sort of a reaction wheel here and add. So we're going to add H2 first. Now if you add hydrogen, usually with a, we'll say platinum catalyst, it doesn't cost any more since we're just writing it. Usually what'll happen is you just get the alkane. You eliminate the double bond and you would just end up with ethane. You add bromine across there, you're going to get bromination. You would get you would add across the double bond. The rules get more complicated if it's not symmetrical, but particularly with HBr and the water. But in this case, you just get a single bromination, so you get CH3, CH2, Br. And then adding water, we would get an alcohol, in this case, ethyl alcohol. But you get an OH, it adds a hydrogen from the water to one side and the OH group to the other side, producing an alcohol. So you get several different possible reactions, and those are all addition reactions. We're adding it across double bond, eliminating the double bond, and creating new single bonds. All right, let's talk about aromatic hydrocarbons. They have delocalized structures and are very closely related to benzene. Are there other types of aromatic rings? Sure, but this is a general chemistry class and we'll focus on benzene and its cousins. The pi electrons are represented as a circle in the center of the ring because the alternating single and double bonds, which we call conjugated, are delocalized electrons. A lot of aromatic rings do have common names. And even though they do contain pi bonds, they do undergo what we call substitution reactions, which we'll say for a later course more readily than the addition reactions we saw for others. So if I wrote benzene there and tried to add hydrogen across the bond, that would be a big fat no reaction. For example, benzene can be treated with nitric acid in the presence of sulfuric acid catalyst, and we can produce nitrobenzene, but I don't interrupt the double bond structure because it is extremely stable. Here are some examples. So we see benzene, we see those alternating single and double bonds. And you can see that, and then you can see if you had a methyl group, it's toluene. If you had an OH, it's phenol. If you had an NH2, like it's an amine, you get aniline. If you had two methyl groups, we call it xylene, and you have 3 different substitutions of that. And you can have fused ring structures. For example, this is naphthalene, for example, in mothballs. Now, as we were mentioning, this sort of ring is going to be considered to be equal to this ring. And so we just draw a circle indicating all the electrons. But if we were to do one of those addition reactions, we get no reaction. You have to engineer a substitution reaction, but you're not going to eliminate these double bonds because it's very stable structure.